In this video, we're going to discuss neutralization reactions, or the reactions between acids and bases. Arrhenius originally defined the concept of acids and bases in terms of their ability to change the concentration of hydrogen ions or hydroxide ions in an aqueous solution. So, if you simply describe an Arrhenius acid as anything that increases the H plus concentration in solution, that meets his definition of an acid. And in this case, an example would be taking the gas hydrogen chloride and dissolving that in water, which then dissociates into hydrogen ions and chloride ions, greatly increasing the amount of hydrogen ions that are present in the aqueous solution. On the other hand, an Arrhenius base is a substance that increases hydroxide ion. An example of this would be lithium hydroxide, which is a solid. Dissolve that in water and you produce an electrolyte solution, which produces lithium ions and hydroxide ions, hence a base. In addition to ionic species which can act as strong electrolytes, we can also have certain molecular compounds that, when dissolved in water, also act as bases and therefore increase the hydroxide ion concentration. An example of this is if we were to take the gas ammonia and dissolve it in water. It actually reacts with water molecules to remove an H plus ion from the water molecule, to therefore producing this equilibrium that you see here, in which we have produced the ammonium ion and hydroxide ions, and hence increased hydroxide in the solution, and that meets the definition of a base. So, this is actually a weak electrolyte because of the fact that it is an equilibrium situation where only a small fraction of the ammonia actually reacts with the water to produce the ammonium ion and hydroxide. Unfortunately, the Arrhenius definition is somewhat limited in its ability to describe all of the acids and bases that we know of at this point. And so to come up with a better way of describing acids and bases, we need to understand the so-called Bronsted-Lowry theory for acids and bases. So in terms of what makes a Bronsted-Lowry acid or base, in this case, we have to talk about the transfer of hydrogen ions from one species to another. And so an acid is something that is able to give up a hydrogen ion, and a base is something that is able to accept a hydrogen ion. At this point, we want to discuss our ammonia reaction with water and how it might be related to the Bronsted-Lowry acid-base theory. Again, we are looking for the transfer or the donation of a proton, so that we are focusing on which species is giving up an H plus and which species is accepting that H plus. So, in our reaction that you have shown here, which we discussed as the equilibrium between ammonia and water, producing ammonium ion and hydroxide ion, the hydrogen ion is given up by the reactant species water and transferred over to the base, which is the ammonia in the on the reactant side of the arrows. So the water is acting as the acid because it is the proton donor, and this is then consistent with the ammonia accepting that proton and acting as the base. Previously, we talked about the hydrogen chloride forming an acid solution in the Arrhenius definition. So if hydrogen chloride gas is bubbled through water, it produces hydrogen ions, and chloride ions in solution because it's a strong electrolyte. It increases H plus in the solution and meets the Arrhenius definition. On the other hand, if we discuss it in terms of proton transfers, in this case, the hydrogen chloride is going to act as the acid by donating an H plus to a water molecule, and so the H plus is transferred from the HCl to the water, and so the water acts as the base and the HCl acts as the acid. In this particular case, the products are a species which is known as the hydronium ion, H3O+, and then the other species is chloride. It turns out that water has a really interesting role in all of these reactions because in the reaction that you see here with the ammonia, the water is acting as an acid by transferring a proton to the ammonia, whereas in the reaction involving the HCl, the water could act as a base. This is a fairly interesting situation where we have a chemical species that is amphoteric. It can act as either the acid or the base. At this point, we need to make sure that we understand some of our nomenclature here in terms of what these terms mean. And so the first is, what is the definition of a strong acid? A strong acid is a strong electrolyte, and typically the reaction between water and a species such as hydrogen chloride is going to be written with a single-headed arrow, meaning that all of the reactants are converted into the products, and this is not an equilibrium. So when we take hydrogen chloride gas and dissolve it in water, we end up completely with hydronium ions and chloride ions present in the solution. So a strong base, likewise, when dissolved in aqueous solution, will completely dissociate or ionize to produce the corresponding ions in the aqueous solution. As an example, lithium hydroxide dissolves to produce lithium ion and hydroxide ion, and is again written as a single-headed arrow. There is none of the LiOH actually present in the aqueous solution. At this point, I need you to memorize the small number of compounds that act as either strong acids or strong bases. You can see the list here. So there are 6 strong acids: perchloric acid, sulfuric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and nitric acid. And likewise, there are 6 strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. So any species that is not a strong acid, but then will generate some small portion of hydrogen ions in solution, fits the criteria for being a weak electrolyte, and these are referred to as weak acids. So a good example of this might be something like hypochlorous acid, HClO, which acts as an acid by transferring hydrogen ion to a water molecule, producing hydronium ion, but in this case only a small portion of the HClO does this, and the other product, of course, is the hypochlorite ion. You'll notice that this reaction is written with the double-headed arrow because it's an equilibrium. This reaction is known as the net ionic equation for this reaction, and so this is a concept that we'll have to explore more in the future here. Conversely, if we have a species that acts as a base by generating hydroxide in solution, but only a small portion of the base is producing the hydroxide, then this is a weak electrolyte, and we refer to these as weak bases. If it's not a strong base, it must be a weak base. And so in this case, the ammonium ion meets this criteria, or the ammonia reacting with water meets this criteria, and only a small portion of the ammonia produces ammonium and hydroxide in solution. So this is also a net ionic equation. So now if you have memorized your strong acids and strong bases, we can see how well you can do this. So if we were to try to classify the following formulas as either strong acids or strong bases, or weak acids and weak bases, we can start with the first compound here, H3PO4. This is not one of the strong acids, but is phosphoric acid is actually a weak acid. H2SO4, though, is a strong acid. And sodium hydroxide is a strong base. Aluminum hydroxide is not one of your strong bases, therefore it has to be a weak base. HClO4 is one of your strong acids. And then finally, HCN, hydrocyanic acid, or in this case, probably the best name is that. This is a weak acid.